So the primary use of vectors is connecting one place to another, or using them as strings in order to connect two pieces or two places on a grid in 3 dimensions and determine the length between those two places. So I'm just going to make up 2 random spots in 3 dimensions. So we'll pick point 1 is at 3 on the x, minus 8 on the y, and 12 in z. And place number 2 is at minus 1 on x, minus 7 on y, and 4 in z. Okay, so point 1 is here somewhere, and point 2 is over here. And what I'd like to know first is how I get from point 1 to point 2. So the way you do that, so let me write that out in English. How do you get from P1 to P2? Okay, so there are a few ways to do this. I want to do it just logically first, so that you can see that this isn't algorithms. That vectors are really easy to do if you take a minute to figure out what it is it's asking you. The calculations are not hard, but knowing which calculation to do sometimes can be a little daunting. So if I'm trying to get from here to here, you're just talking about changing your coordinates. So for example, if I started at point 1 where the x value was 3 and I had to get to point 2, which is at -1, I had to go 4 to the left in x, right? This number has to drop 4 in order to get to this value. So the vector I need to follow has to go -4 in the x direction in order to get from 3 to -1. In order to get from -8 to -7, I have to increase by 1. And in order to get from 12 to 4, I have to drop by 8. So I mean that should be it, right? That's all you really need to do. And the way you can confirm this is to take P1 and add these coordinates and see what you get. So point 1 was 3, -8, 12, and I've got this thing I just constructed. So 3 plus -4 would be -1. -8 plus 1 would be -7. And 12 plus -8 would be 4, which happens to be P2. So if you go from the origin to P1, travel along this vector, then you end up at P2. So I have this thing in pink here, which is telling me how to get from this location to that location. So I'm going to draw that in there for you. This vector is -4, 1, -8. So you have some instructions to get from point 1 to point 2. What's maybe more interesting, and up until this point would have been almost impossible for you to calculate, is I want to know how far apart those 2 dots are in a 3-dimensional space. So if you've ever tried to put up a roof truss or like a rope ladder or a clothesline from one place to another place that goes off in 3 dimensions, it's very challenging to measure that straight line because you have to drag a tape measure from one inaccessible place to some other inaccessible place and have it not sag, right? Like, it's just a whole mess. But here, I gave some coordinates for a random place, and I gave some coordinates for some other random place, and we drew the vector between them. If I have that vector, its magnitude, right, like the length of this line, is the distance between point 1 and point 2. So now that I have it, if I just took the magnitude of that vector, I would know how far apart these points are. So I'm gonna do that. How far apart are P1 and P2? Okay, so in order to do that, I'm going to have to take the magnitude of -4, 1, -8. And the magnitude of that thing squared, this is just the Pythagorean relationship, is the x-coordinate squared plus the y-coordinate squared plus the z-coordinate squared. So this thing, -4 times -4 is 16. 1 times 1 is 1. 8 times 8 is 64. 16 plus 64 would be 74. 80 plus 1 is 81. And since this thing is squared, to get my final answer, the magnitude of -4, 1, -8 is going to be the square root of 81, which is 9 units. Whatever unit I'm using. Maybe these are centimeters in x, maybe they're meters, maybe they're just ticks on a number line, I don't know. Doesn't matter. But there's 9 of them between this dot and this dot. So if you can take a minute to appreciate what you've accomplished here, you took one random place in space, right? Like here. I know you can't appreciate that because you're watching it on a flat screen, but you can grab spots in 3 dimensions anywhere. You took P1, you took P2, and you calculated how far apart they are based on their coordinates. That's very powerful because it lets you start to calculate distances that you can't do with tape measures, right? Like bridges, you can't build or you can't measure with a tape measure the span of the Saugeen River. Like, you just can't do it. You can't measure the distance between Toronto and Montreal with a tape measure. You can't calculate the distance between Earth and the Moon with a tape measure, but you can assign them coordinates based on where they are on the planet or based on where they are in space, and then use this fact that a vector between them can be determined by just counting coordinates. And then the magnitude of that vector gives you their separation. So suddenly you have the tools to analyze distances between things that are either way too big or way too small to be measured in a standard way. Okay, now if I look at this, some of my notation is a bit cumbersome, right? Like I would like to have some letters here, and I don't want to have to write this every time. So I'm going to do one more example of this particular type of question, and I'm going to use a slightly different notation. Okay, so same idea, except instead of calling it point 1 and point 2, I've used vectors A and vector B. So if I were to draw that for you, I need some sort of origin, right? Some sort of starting place where I can measure vectors A and vector B from. So vector A maybe goes like this, and so that's A, and vector B maybe goes like that. Just if you can appreciate for a minute that in these diagrams, where I drew these has nothing to do with the coordinates, and it doesn't really matter. You're just trying to represent that there's 2 lines flying off in 3 dimensions. And this question here, how do I get from A to B? Well, if I'm trying to do that, I'm trying to get from here to here. Now, I'm going to give that vector a name. You notice I had numbers in here, like in pink, and then I had to use the magnitude symbols on a bunch of numbers, and I didn't like that. So I'm going to introduce a symbol for you. The vector that goes from A to B is like this. A, B, with a big vector across it. So that thing, if you see that, 2 letters with the big vector arrow over top means from this to that. Okay, so if I'm trying to get from A to B, in the last example I asked myself how I get from here to here, right? So to go from 6 to -3, I'd have to drop 9. Okay, so I could get that number calculating wise by taking my endpoint, -3, and subtracting where I started. So -3 minus 6 gives me -9. That's the number I want. To get from here to here, it has to be up 2, and you notice that 4 minus 2 is 2, so that's good. 2 minus -8 would be 10. This number has to arise 10. What I'm doing is a classic delta kind of calculation where the change in something is what you end up with minus what you started with. So if you have $10 in your bank account now and you started with $2, then the change would be 10 that you have now minus the 2 that you started with. Your bank account increased $8. So to get from A to B, the way you calculate this, sort of, if you want a formula, is you take your endpoint, the place where you stop, and then you subtract the place where you started. So in this particular example, A to B would be, lost my green marker, coordinates of B, -3, 4, 2, minus the coordinates of A, 6, 2, -8. And so the vector connecting A to B would be -3 minus 6 is -9. 4 minus 2 is 2. 2 minus -8 would be 10. There you go. So this next question, how far apart are P1 and P2? I'm going to rephrase this as determine the distance between A and B. That's not a different question. It's phrased differently, but it's asking you for how far apart those things are. Well, I already have the vector that connects A to B, so I already have the instructions. I just need the magnitude of those instructions in order to figure out the distance. So the magnitude of AB squared would be -9 squared plus 2 squared plus 10 squared. So the magnitude of A to B is 81 plus 4 plus 100. So the magnitude of A to B squared is 185. Therefore, the magnitude from A to B is the square root of 185. And as we discussed in the last section, this is a perfectly acceptable answer. You don't need to evaluate that as a decimal. You can just leave it as the radical in the radical form. So determine the distance between A and B. This little block here of symbols says the distance between A and B is the square root of 185. Okay, good. So this is pretty straightforward with numbers, and it does give you the ability to measure and calculate distances between points that are otherwise inaccessible. What's also very powerful about it is that you can do this without numbers at all, and you can just use vector proofs to try and prove that some things are multiples of others. So we're going to do a few examples of these kind of calculations in abstract. So I've put some lines on this diagram, and this example is from the notes, so you should be able to find this diagram written up if you scroll up a little bit on the page. Each of these locations, A, B, C, D, E, and F, are corners of this wonky looking shape. And I have some arrows on there to show that some of these are parallel. Like these two lines are parallel and these two are parallel. And then these two are sort of off on their own. So there's some things I'd like to point out to you about these vectors. So first off, do you notice that if you go from A to B, you travel along this line and you go that far? If you go from F to E, you go the same distance, so the same length, and you're going on a parallel path. So if you were going from A to B and that required you to go up 1 in X, up 2 in Y, and up 3 in Z, if you followed those same instructions from F, up 1, up 2, up 3, you would travel exactly the same length and in exactly the same direction. So you can say from this diagram that because A to B and F to E are the same length and parallel, that they're equal to each other. So I'm going to write that down here underneath. A to B is equal to F to E because they are parallel and the same length. Okay, good. So if I were to look at the other two that are parallel, F to A and E to D, they're going in the same direction, but D to E is not as long as F to A is, so it must have slightly different instructions. So based on this diagram, you can state that F to A is not the same as E to D because they are not the same length. Okay, now even if I went and I put a little tick mark on this piece here and this piece here to say that F to A and C to B were the same length, you can tell by the diagram that this is not traveling in the same direction as that. So like this statement, I can write another one underneath saying that F to A is not the same as B to C because they are not parallel. Okay. Good. So another statement I want to try and make here is A to B is equal to F to E So what if you asked yourself, is A to B the same as E to F? So if I go from A to B, is that the same as going from E to F? It's the same distance, and they're parallel. But in A to B, you go from left to right on this diagram. And E to F, you go from right to left. So it's the same length and it's parallel, but it's in the wrong direction. So this thing here is also false. From here to here is not the same as here to here. If I were to try and fix it, I would need to go this way, right? I need to go backwards on E to F. And the way you get yourself going backwards on a vector is to make it negative. So if I were to change that, A to B is not equal to E to F because A to B is equal to negative EF. So A to B is equal to this if you travel backwards on E to F. Now, E to F means the vector from E to F. So if I go the other way, backwards would be from F to E. So I could write this in there as well. Because we'd said that earlier, right? A to B is the same as F to E. So do you notice what's happened here? That if I have a vector from this place to that place, and I want to switch it, I can either switch the order of the letters, or I can put a negative in front. So if I had something like this vector here, from B to C, going this way, that vector is the same as going backwards on the vector connecting C to B. Now this is just a basket full of rules, a basket of how to play with the notation. So if you have a negative in front of a vector, you can just switch the letters, and then you've got a positive version of that particular vector. Another sort of interesting thing here is I can put a new random point on this particular diagram, or I can just use a point that's there originally. So I have this vector here from F to E. Well, that vector gets me from here to here, and that would be the same as if I went from F to A and then A to E. Right, I'd end up here, right? Whether I go from here to there, or whether I go from here to here, here to here. In both cases, I started at F and I ended at E. So you can take vectors, what I have there, had F to E, and I can write that as the vector from F to A and the vector from A to E. Do you notice that that's allowable as long as these two things are back to back? And in fact, I can spread it out even more, right? I could get from F to E if I went from F to A, and then from A to B, and then from B to D, and then from D to E. Right? F to A to B, B to D, D to E gets me to the same location as if I went straight from F to E. And again, you notice in my construction there that those two are back to back, these two are back to back, these two are back to back. So I have a nice continuous path. And there's nothing stopping me even from inventing a new random point like k up here. So I could do f to e is the same as f to a plus a to k plus k to e, maybe. And so there is no line connecting k to e, but I could do that. I could go from here to here to here directly to there, and it would get me from this place to that place, just in a different number of steps. So we're going to use this sort of set of facts in order to do some geometric proofs. So I'm going to have to clean this off and give me a minute while I draw you a hexagon. Okay, so this diagram is drawn for you in the notes. Again, look up and you can read through this. I've drawn for you a regular hexagon, or I attempted anyway. So this is a shape where all 6 sides are of equal length. So if I were to go through and make a list of facts that are true about this particular hexagon, I could say that the vector from A to B is equal to the vector from E to D, because they are the same length and they're parallel and they head in the same direction. By exactly the same logic, I could say that the vector from C to B is identical to the vector from E to F. And I can say that the vector from F to A is identical to the vector from D to C. Because they're the same length, they are parallel, and they're both going in the same direction. Now, there is another fact that you can prove, that this vector here from D to A happens to be twice the vector from C to B. So I'm just going to give you that for now. And once we do a few examples, this is a question in the problem set attached at the end of this, is to try and prove that this is true in an equilateral hexagon. Okay, good. So the next section is trying to define vectors from one place to another in this particular shape in terms of other vectors in the shape. So the first thing we're going to try and define is write A to E. So that's from here to here in terms of vectors on the edges of the shape. Okay. So, what exactly is that asking you to do? Well, I can see the path I'm supposed to follow from A to E. I want to get from there to there. But instead of crossing through empty space, I want to try and do it along the edge of this hexagon. So if I'm trying to get from A to E, well, I could do that by going from A to F and then F to E. Well, and then you're done. So that was pretty easy. So the next example that's in those notes is trying to write this vector, A to D. So AD in terms of edges So if I'm trying to get from A to D, I could go from A to F, F to E, E to D, and I would have done so on the edge of the hexagon. Or I could go from A to B, or B to C, or C to D, and I would end up at the same place. So we went this way for the first example. Let's go that way for the next one. So A to D equals A to B plus B to C plus C to D. All right, good. So next one, I want to try and define A to F. That's from here to here in terms of FE and BA. Now that's kind of weird, right? Like, why would you want to do that? Well, it's possible that you have some sort of engineering problem and you know something about this particular segment and you know something about this particular segment, and you're hoping, cross your fingers, that you can express this in terms of the two pieces you know. So how am I going to do that? Well, first thing I'm going to do is I'm going to try and draw a loop that contains AF, FE, and BA. So if I can erase this particular thing here, I'm going to go, so from A to F, I want to get through AB and I want to get through FE. So I'm going to do this. I'm going to go from A to B, B to E, E to F, and F to A. So if I write that out, this vector I'm trying to define, A to F, is the same as A to B plus B to E plus E to F. Okay, good. So here's my loop, A to F, to get from here to here. I can do it that way, or I could walk around this funny path. So if I do that, I'm going to go look back and I'm going to see what I was asked to define this in. I was asked to keep FEs and BAs. Well, I have an AB and I have an FE. So this thing here, AB is not the same as BA. It's negative BA. So if I want to flip these two letters to turn this into that, I'd end up with negative BA. This thing here, an E to F, well, that's almost an F to E. It just goes the wrong way. So I'm going to do the same thing to this, minus F to E. This thing here, I don't have anything left, so I'm going to just write her in. And this over here, I was allowed to keep, so I'm just going to keep that. Now you notice that this, and this were all in the list of things I was asked to use. The only thing I've got to get rid of now is this vector from B to E. So B to E, well, that's one of these diagonals. And if D to A happens to be twice this, then B to E is going to be twice that. So I'm going to make that replacement, that B to E is the same as two A to F's. So this was already here. This was already here. I'm going to replace B to E with two A to F's. This minus F to E was already here. Now you notice I have AFs here and AFs there. I'm going to bring this over so that all of my AFs are together. So I have AF plus 2AF on the other side would be minus 2AFs minus BA minus FE. So one of these minus two of them is -1 AF. So if I multiply through by -1, -1 times -AF is just AF. This would be just BA, and this would be just FE, positive. So what I've done there, right, if you look at it, is I've defined AF in terms of FE and BA, just like the question asked me to do. So, what? If I take this little diagram and I lift the vectors here, B to A is this thing going like this, right? Straight to the left. So BA is like this. Now F to E goes like this, right, on a 60-degree angle. So if I go parallel, should have written that on top. That's B to A. If I travel along B to A, like this, and then along F to E, like this, allegedly, I get a vector that's equivalent to AF. So if I just look at this diagram, ignoring the hexagon for a minute, this plus this gives me that. So if I go find AF on the diagram, I should find over there on the hexagon something that's about that long and is heading down and to the left. And if I find AF on there, well, there it is. It's about that long, heading down and to the left. So A to F goes this way. So did this vector here. So you've been able to define the length and direction of this edge using two other edges in this particular shape. Now this is a bit of an abstract exercise, and when you go to do these, they're a little stressful to get going. But you have to trust me that once you do a handful of them, you start to get the rhythm. So the basic idea is if you're asked to define something in terms of two other edges, try and draw a loop. And try and draw the shortest loop you can that contains all of the pieces that you're asked to use. Once you've drawn that loop, write out how you did it, and then examine each piece that's in that loop and try and transform them into the two pieces that you were asked for. This one, for example, if I just flipped the letters and made it negative, gave me one of those things. Same here. Then I had to be a little more creative with this vector B to E. I had to go dig through the definitions, and I had to try and logic how I could replace B to E with either one of these, one of these, one of these, or some combination of them. Turns out by definition that this happens to be twice that, made the replacement, gathered like terms, and then I was done. It's an interesting sort of feature about shapes that this is a two-dimensional object, right? It's flat. If it's two-dimensional, that means you only need two pieces in order to know every piece of information about it. And so if you notice what's happened here, this side, the down and left one, I was able to define that with two sides that don't go in the same direction. I only need two because it's a two-dimensional shape. So I can use that side and that side to go back, and I could try and define D to C in terms of these two vectors, and I'd be able to do it. I could try to define A to D in terms of those two vectors, and I'd be able to do it. So go to the practice problems, take a deep breath, find your Zen space, and give them a try. And I promise you that after you've done the first 4 or 5, that this will start to make some sense.